Hello APC Mechanics students, in Unit 3, Work, Energy and Power, Class 3, 3.1 Work, Part 3. Section 1, Work done by a variable force. Previously we have introduced the work done by a force F along a displacement D in the form of a dot product as work is F dot D. However, this relation can be used if and only if the force F is constant in direction and in magnitude. In the general case where F is either variable by direction or magnitude, then the work done is given as a line integral, where dx is the differential displacement along the x direction, xi is the initial position, and xf is the final position along the path of the work done by the force. So basically, we have introduced previously the work to be F dot D. However, this is we're assuming here that F is constant in direction and in magnitude. If F is variable in either direction or in magnitude, this should be upgraded to an integral form, where D would be replaced by a differential displacement from an initial position to a final position, where xi is the initial position and xf is the final position. In a two-dimensional space, the force and the differential displacement are given in terms of the components as dr is dx plus dy and f is fx plus fy. Then the work done by the force would be as that. So here what's happening is the following. Now, the force F is given by the component Fx and Fy, and dr is given by the components dx and dy. So if we're doing the dot product of F dot dr, that would be Fx multiplied by dx plus Fy multiplied by dy, and now we can integrate here, we integrate here, we integrate here. The boundary is here from initial position to a final position. Here would be initial horizontal position, final horizontal position, initial vertical position, final vertical position. So let's recall that what's the difference between these two definitions of work. This is a general one, you can always follow this one. It offers more features, and more importantly, we can use it whenever the force is a function or variable in both direction and or magnitude. This can be used whenever the force is constant in magnitude and in direction along a certain displacement. Example 1, the constant force F with components Fx is 3 newtons and Fy is 40 newtons shown above acts on a body while that body moves from the point P to the point Q, given by the corresponding coordinates. How much work does the force do on the body during the process? So at the first glance, you might think that because the force is constant 3 and 4 in magnitude and in direction, this means that we should use the work to be F dot D. However, we're going from the point P to the point Q, and that the path is not defined. For this reason, we need to use the integral form given by F dot dr, and we can represent it along the horizontal as a sum between the horizontal and the vertical integral. Now, what would be the initial position? 2 meters to a final position of 4 meters. Here I'm talking about the horizontal because in the text they mentioned we're going from P to Q. So that would be 2 and that would be 14, and for the vertical that would be 6 and that would be 1 because we're going from 6 to 1. So one common mistake is to place 1 here and 6 here, taking into consideration that 1 is less than 6, but this is completely wrong. The boundaries are always set by the path. So P is the initial position and Q is the final position. For this reason, this is 2, this is 6, that would be 14, and that would be 6, and that would be 1. Now, the x component is 3 multiplied by dx, the y component is 4 multiplied by dy. Now what happened here is the following. Let me do one of the integrals. So 3 can be dragged out, that would be 3 integral from 2 to 14 dx. Now we're integrating over dx, that would be 3 multiplied by x from 2 to 14. Now 3 is a factor, it can be taken out. Now we replace x by 14, that would be 14 minus 2. So which is this expression. Let me also do the other one. So 4 can be dragged out, that would be 4 integral from 6 to 1 dy. So 4 is a factor multiplied, so the constant would be a linear from 6 to 1. So first we start by replacing 1, which is the final, minus 6, and that would be 4 multiplied by minus 5. and the final answer would be 16, and the unit of W is joules. Now section 2, the work done by linear spring. In this section we will investigate the work done by the tension exerted by linear spring governed by Hooke's law given by Kx. The block oscillates around the equilibrium position O under the action of the tension force given by Fs. So the equilibrium position would be the position where if we leave the block, it will rest at this equilibrium position while the spring is unstretched. Or you can think about it, if this is perfect, then it would be the point which is midway between the extreme position. Here we're considering that there is no friction between the block and the surface, so the spring will oscillate forever. Now we can consider the motion of the block from B to O. So we're assuming that the block is moving from B to O. Actually, if the block starts from B, oscillates to the left, and reaches B back again, this motion can be divided into 4 identical quarters. The first quarter while going from B to O, the second quarter while going from O to C, the third quarter while going from C to O, and the fourth quarter going from O to B, in order to perform one complete motion or oscillation. Now we're interested going from B to O. We will discuss what will be the work done by the tension force. And whenever we're talking about work, now we're just interested in the descriptive part. So I won't refer either to the dot product or to the integral form. Now going from B to O, the displacement is to the left, and the tension would be to the left. Why? Because the spring will push the block toward the equilibrium position. The tension always points toward the equilibrium position. Now in this case, because the displacement and the tension are in the same direction, then this means that the work done by the spring is positive. Why? Because if we refer to the dot product, for example, the work is F dot D. So the work done by the force is positive whenever the force and the displacement are pointing in the same direction. It's negative while they're pointing in opposite directions. So going from B to O in the first quarter, this means that the work done by the spring is positive. Now going from O to C, so that would be the point C, and we're going now from O to C, so the displacement is still to the left, but in this case the tension would be to the right because the spring will try to push the block toward the equilibrium position. In this case, the displacement and the tension, they are in opposite direction, which makes the work done by the spring to be negative. Whenever I refer to the work done by the spring, I mean the work done by the tension force, because spring is tension. Now from C to O, now we're in the third quarter, so let me say this is the first quarter, second quarter, third quarter. Now in this case the direction of displacement is to the right, and the direction of the tension would be to the right because the spring will be pushing the block toward the right. In this case, the displacement and the tension, they are in the same direction, which makes the work done by the spring to be positive. Now going from O to B, which is in the final quarter, now the displacement is to the right while the direction of the tension would be to the left toward the equilibrium. D and F as have opposite direction, which makes the work done by the spring is negative. So whenever we're talking about oscillations of a spring, the work done is pretty complicated. The work might be positive, the work might be negative. This depends on the displacement and the direction of the tension. Notice that the tension in this case is a not constant force for a very simple reason: the direction is not constant. The direction of the tension is always pointing toward the equilibrium position. Okay, so for this reason we can differentiate between positive work and negative work. The work would be positive whenever the spring is moving toward the equilibrium position, which is O, and this happens in the first and the third quarter if we started from the point O, from the point B, which is indicated here. However, if the block is moving away from the equilibrium position, the work done by the spring would be negative. So let me do a recap. If we're moving toward the equilibrium position, the work done by the spring would be positive. If we're moving out, so we're moving toward the equilibrium position, the work done by the spring is positive. If we're moving away from the equilibrium position, that would be a negative work. And this is represented here. If the block is displaced toward the equilibrium, then the work is positive. If the block is displaced away from the equilibrium, then the work is negative. The work done by the spring should be expressed as an integral because, for a very simple reason, the force is variable in direction. Now what about the magnitude? The force is expressed in terms of the position given by kx, the position along the oscillation changes, which makes f to be variable also in magnitude. So this reinforces the fact that the work should be expressed as an integral. Because f is variable both in magnitude and in direction, as we have stated, in order to count for the positive and negative sign due to the positive and negative work done by the spring. So how we're gonna solve that problem? So we need to take into consideration what's making it positive and negative. It happens that in order to solve this problem, the integral should be represented, the force inside the integral should be represented in terms of the restoring form. If you remember in Unit 2, either in Class 1 or Class 2, we have introduced the force of a spring in terms of its restoring form, which is given by minus kx, and we've said that this minus sign is due to the restoring force exerted by the spring. What does it mean to be a restoring force? It means that the force exerted by the spring will always try to push the block toward the equilibrium position. So we have two forms of the force exerted by the spring. The first one, which is the usual one, which we use it in the FBD, this is given by the magnitude. And we don't place any minus sign because we know the direction of the force exerted by the spring, and we're representing it in the FBD. However, in a dynamical way, if you want to do calculus, which is basically integral, the force should be represented in a dynamical form, which is given by the restoring form, and we should include the minus sign. Then let me repeat, if we're doing, for example, Newton's second law, and we're doing an FBD at a certain instant, no need to place this minus sign, because it is for a specific instant and we know the direction. So we can use just simply the magnitude. However, if we're interested in calculation where the system is evolving and we're dealing with a differential or an integral form, the force should be represented in a restoring form, including the minus sign. In the vector notation, that would be represented as f as a vector is given by minus kx factor. Replacing fs in the integral, we would get the dot product between the force of the spring and dx. So we would have minus k is a constant, would be dragged out, and that would be x dot dx. And independent of the direction of x and dx, we're assuming that they are in the same direction, and that would be minus k integral from initial position to final position x dx. So let me here also state something very important. If we're talking about the vector x, so we can define its differential form given by dx. Both x and dx have the same direction, and x dot dx would be simply x dx. Alright? And ws would be minus k integral from xi to xf x dx, where the origin in this case is taken to be the equilibrium position and the positive direction is taken to the right. Now, section 3, linear versus nonlinear springs. Springs in general exert a tension force. These springs might exert a linear tension force or a nonlinear tension force, and this depends whether the spring is linear or a nonlinear spring. A linear spring would exert a linear tension force given by kx. So here I'm not interested in the form, I'm just explaining what is meant by linear and nonlinear. Then why this is considered to be linear tension force? Because the force depends on the position, and the position is linear, which makes this force to be linear force. A nonlinear spring would exert a nonlinear tension force given in different forms, which is not linear in position, like a quadratic, linear term plus a quadratic term, or a cubic term. More important remarks. Remember that whenever we're calculating the work done by a spring, the force exerted by the spring should be represented in its restoring form. And here, there's another important thing. If we're asked to calculate the work done by external force to compress or stretch the spring, then the force represented in the integral form would be just the opposite of the restoring form. So let me state it here. For the work, we can differentiate between two types of works. The work done by the spring, which should So let me state an example on a linear force, which is given by kx. In its restoring form, we should include the minus sign. So here I'm talking the work done by spring, so that would be minus k integral from an initial position to a final position x dx. So this work would represent the work done by the spring. Also, we can talk about the work done by an external force, not the spring, external force, to compress or elongate the spring. That would be W, to be just the integral from xi to xf kx dx. So here the difference between this and that is just a minus sign, and that would be the work done by an external force to compress or stretch the spring. Alright, then we're differentiating between two works. If we're talking about the work done by the spring itself, we need to use the restoring form. If we're talking about the work done by an external force, just we put the magnitude. Now example, when a Hawkian spring of stiffness 1 newtons per centimeter is stretched by distance x from its equilibrium position, it produces a force of magnitude given by kx. Now the spring is compressed by distance a from the equilibrium position, so let me explain here what's happening. Now this is the spring, and that would be the equilibrium position. Now what we're gonna do, we will compress the spring by distance a from the equilibrium position. Compression is to the left, elongation is to the right. So this is the initial position, and the final position would be like that. So okay, now what we have done here, we have block initially attached to a spring on a level surface in the initial and at the equilibrium position. We're gonna compress the spring by distance a. Now here you can ask yourself, the work done by the spring would be positive or negative? Would be negative, because we're going away from the equilibrium position. So in part A, they're asking us to calculate the work done by the spring, which is given as an integral form. Now here we ask ourselves, should we use the restoring form or the usual form? Because it's the work done by the spring, then we need to use the restoring form, which is given by minus k. Now what about the boundaries of the integral? We have moved from an initial position given by the equilibrium position. For this reason, this is the origin, and we know that the positive direction is to the right. So we're moving to the left, and that would be minus a, because the position might be positive or negative, and that would be x. So the integral of x would be x squared over 2 from minus a to 0. Minus k is a common factor, can be taken out. So replacing x by the boundaries, that would be minus a, and that would be 0. So that would be 0. And minus a to the power of 2 would be a squared. And let me erase the inking. So k is given by 1 newtons per centimeter, and remember to convert from newtons per centimeter to newton per meter. We should be multiplying by 100. However, from centimeters to meters, we should divide by 100. And k is given by 100 divided by 2. That would be minus 50 a squared. And notice here that the work done by the spring is negative. A squared is positive. So why the work done by the spring is negative? Because we're moving away from the equilibrium position. So that would be x as well. Now we're interested in calculating in part B the work done by an external force to compress the spring, which is exactly opposite to this one, because we're doing work against the spring. So here, as you can see in the integral, we have used just kx from 0 to minus a for the same exact reason. Now that would be quadratic, which is x squared over 2 from minus a to 0. Now factoring out k and replacing the boundaries of the integral, that would be from minus a to the power of 2 to 0, that would be 0. And replacing the value of k, that would be a positive amount of work, which is opposite to minus 50a squared, and that would be just w. Now exercise 1, a particle P is located on the x-axis as shown in the figure. A force exerted on the particle is given by the equation F is kx cubed. So as you can notice that here that F explicitly depends on the position. As we're doing the displacement, the magnitude of F changes, which means that if we're interested in determining the work, we should do it as an integral. Indeed, they're asking us to calculate the work done by the force in moving the particle from an initial position 2 to a final position 1. If you notice, the choices are given by positive, so no need to worry about the minus sign. Then the work done would be given by integral from an initial position to a final position given by f dot dx. Now the initial position is given by 2, the final position is given by 1, the force is given by kx cubed dx. Now k is a constant, which is 4, can be dragged out from 2 to 1, x cubed dx. Now the integral of x cubed would be quartic. We increase the power and divide by the final power, so that would be 4 x power 4 divided by 4 from 2 to 1. Now we can factor out, so here 4 and 4 they would cancel. That would be just simply x to the power 4 from 2 to 1, which means 1 to the power 4 minus 2 to the power 4, which makes it 1 minus 16. That would be minus 16 joules. And the correct in 15. Then the correct answer in this case is A. Now exercise 2, for a particular non-linear spring, the relationship between the magnitude of the applied force F and the resulting displacement x from the equilibrium is given by kx cubed. So what is the amount of work done by stretching the spring a distance x0? So notice that among the choices we're not interested in the minus sign. Because the force is variable, we need to set the work as an integral. That would be the work from an initial position to a final position of f dot dx. The initial position is given by, so what is the amount of work done by stretching the spring a distance x0, knowing that we started from the equilibrium, which is 0, to x0. So y plus x0 because we're stretching. Now kx squared dx, we can take k out. That would be k, the integral from 0 to x0 x squared dx. Now we're ready to integrate. Now we increase the power, that would be 3, and we divide by the final power, which is k x cubed over 3 from 0 to x0. We can factor out k over 3. That would be k over 3 x0 cubed minus 0 to the power of 3. So that would be 0, and the correct answer in this case would be E. Now exercise 3, when a certain spring is stretched by an amount x, it producing a restoring force given by F is minus ax plus bx squared. Now here notice that this force is represented in the form of the restoring force. Now how much work is done by an external force in stretching the spring by an amount d from its equilibrium position? They're asking us for the amount of work done by the external force, which is opposite to the work done by the spring itself. However, now we can determine the work done by the spring, and the work done by the external forces just would be up to a minus sign. Now the work done by the spring, because the force is variable, should be represented in the form of an integral given by W of the spring is given by initial position to a final position of F dot dx, which is given by the initial position is given by the equilibrium. The final position is given by d, either plus or minus. This depends whether we're stretching or compressing. We're stretching, so that would be plus d of the restoring force given by minus ax plus bx squared multiplied by dx. Now we can split this integral because we know that the integral is distributive over the addition and subtraction. That would be, so minus a is constant, can be dragged out, and b is a constant, can be dragged out. So the linear would give us quadratic, dividing by the final power from 0 to d, plus b, the quadratic would give us cubic from 0 to d. Now you can factor out minus a, and that would be d square over 2 minus 0 square over 2, so we can ignore this one, and that would be minus a d square over 2. Now what about this one? B over 3 can be factored out. That would be d cube minus 0 cube. This can be ignored, so that would be plus b over 3 d cube. Now this represents the amount of work done by the spring, but we are interested in the amount of work done by the external force, which is opposite to the spring, and the correct answer in this case would be C. So basically it would be minus the work done by the spring, which is minus of minus a d square over 2 plus b over 3 d cube, and that would be a d square over 2 minus b over 3 d square, and this is d cube. Now exercise 4, a block of mass m is on a rough horizontal surface. Rough, it means that we have friction, and it is attached to a spring with a spring constant k. The coefficient of kinetic friction between the surface and the block is mu. When the block is at position x is 0, the spring is at its unstretched length. The block is pulled to a position x is given by x0 as shown above and released from rest, so the speed here is 0. The block then travels to the left, so the displacement is to the left, starting from an initial point here, and passes through x is 0 before coming momentarily to rest at the position x is minus x0 over 2, and this is the final point, which is 0 before it changes direction back again. So why the spring didn't reach an asymmetric extreme position given by minus x0? Because we have friction, so the amplitude of oscillations will decrease. Which of the following is the correct expression for the coefficient of kinetic friction mu? So we're interested in the kinetic friction mu. You might think about it as a two approaches: energetic approach using the work energy theorem, or Newton's second law. Newton's second law here would be super difficult, so we're gonna do the work energy theorem, which is delta K is equal to the work done by the external forces. Notice that you need to mention here, if this is a free response, that apply the work energy theorem. Now what are the external forces acting on the block? We have the pull of gravity down, we have the normal push is up, we have the friction to the right because the displacement is always to the left, going from initial to a final position. Now what about the spring? In the first quarter, or in the first part, that would be to the left, and the second part that would be to the right. Now independent of the direction, this can be solved using the integral 4. Here that would be in the first part, so the tension would be toward the equilibrium position. Now what about the variation in the kinetic energy? If initially the speed is 0 and finally the speed is 0, which makes the final kinetic energy to be 0 and the initial kinetic energy to be 0, which means delta K is 0, and the work done by the external forces, that would be the work done by gravity plus the work done by the normal push plus the work done by the spring plus the work done by the friction. Eventually these two are 0. So we're left with the work done by the spring plus the work done by the friction. The work done by the spring would be dealt alone. Now here they didn't mention the type of the spring. For this reason we're gonna take it to be an ideal spring, and this is given by minus K integral for x dx from an initial position to a final position. And the work done, okay, what is the initial position? We're in the positive direction, which is x0, to a final position given by minus x0 over 2 x dx, that would be minus K as a factor, x would be x squared over 2 from x0 to minus x0, minus K as a factor, that would be minus x0 to the power of 2 divided by 2 minus okay, k x0 squared divided by 2. So here I have done a mistake. That would be minus x0 over 2. So minus x0 over 2. So that would be over 2. Let me just do it carefully. Okay. Now x0 minus x0 over 2 to the power of 2 divided by 2. That would be x0 square over 4 divided by 2, which is basically x0 square divided by 8. Minus x0 square divided by 2. Now here we can factor out, or you can subtract the fractions. 1 over 8 minus half, that would be 1 over 8 minus 4 over 8, which is basically minus 3 over 8. So that would be minus k into minus 3 over 8 x0 square, which is basically 3 over 8 k x0 square. So 0 would be equal to 3 over 8 k x0 square plus the work done by the friction. Now what about the work done by the friction? The work done by the friction, so would be F dot D, because we're assuming that friction is constant along this displacement. Displacement is to the left, friction is always to the right, then they're acting in the negative direction, so that would be minus F multiplied by D. Now the friction is given by mu k, the normal push is mg, and the displacement d. What about the displacement? Now d would be the value of the displacement, which is basically this part and this part, which is half plus 1, and that would be half plus 2 over 2, which is 3 over 2. So the displacement would be 3 over 2 x0. Okay. Now moving this to the other side, that would be 3 over 8 k x0 square equals mu k mg 3 over 2 x0. x0 with x0 they cancel, 3 with 3 it cancels, 2 with 8 becomes 4. We're interested in mu k, so mu k in this case would be what? We have k x0 over 4. Basically m is up becomes down, g is up becomes down, so that's given by k x0 divided by 4 mg, which makes A to be the correct answer. And exercise 5, a block of mass m is in a rough horizontal surface and is attached to a spring with a spring constant k. The coefficient of kinetic friction between the surface and the block is mu. When the block is at position x is equal to 0, the spring is at its unstretched length. The block is pulled to position x is x0 as shown above and released from rest. So basically we have the same perfect configuration. This is the initial point and the initial speed is 0. The block then travels to the left and passes through x0 before coming momentarily to rest at position x is minus x0 over 2. So the final position is here. Which of the following is the correct expression for the kinetic energy of the block as it first travels through the position x is equal to 0? So we need the kinetic energy at O, and this can be done using the work energy theorem. Then delta K would be the work done by the external forces. Now what is the initial point and the final point? The final point in this case would be the equilibrium position, so let me erase this. That would be the final point. Now we're interested in determining the kinetic energy at this point. That would be K final minus K initial is equal to the work done by the external forces, gravity, normal push, friction, and the work done by the spring, that would be 0. That would be 0. The initial kinetic energy is 0. So this is 0. Now we're interested in determining the final kinetic energy. The final kinetic energy is the work done by the friction, which is basically F dot D. Displacement to the left, friction to the right, that would be minus F dot D. The friction is given by mu K mg, and the displacement from x0 to 0 as a value would be x0, plus the work done by the spring, which is given by an integral form of minus k from initial position given by positive x0 to the equilibrium position given by 0 of x dx. Now that would be minus mu k mg x0 minus k as a factor, x becomes x squared over 2 from x0 to 0. Now that would be minus mu k mg x0 minus k is a factor. Now 0 to the power of 2 divided by 2 minus x0 squared over 2. So that would be 0. Minus with minus gives you plus. So that would be minus mu k mg x0 plus k x0 squared over 2, which makes C to be the correct answer. Now just a side remark, why my final point has been chosen to be O? Because we're interested in determining the kinetic energy at the point O. Although the final point according to the system is minus x0 over 2, however, if you choose it, you will be dealing with an initial point to be given x0 and a final point to be given minus x0 over 2. So O would be an intermediate point and won't appear explicitly as a kinetic energy. For this reason, our final point can be always chosen based on what is required from us. Then that's it for me in this video, guys. See you soon in a new one.